All right, section 5, we are going to be looking at complex numbers. We're going to be able to review how to use operations and then also talk about what happens when you have complex number solutions. So again, this is a review from Algebra 2. And when we started out working with our first lesson, I showed you this slide with real numbers, talking about all these wonderful numbers that appear on the number line. Well, now what happens if you have a number that does not appear on the number line? More specifically, what happens when your parabola does not cross over your x-axis? Your x-axis is a number line. So when you're looking for solutions and that graph does not cross over, what do? Well, that's where we come into working with imaginary numbers. So when you're thinking about all the numbers that are out there, you have real numbers and then you have these imaginary numbers. No, they're not, it's not like you can't see them, but it's a way that we can actually calculate them and work through some problems, especially because they might come back once you do some operations with them later on. So a review of imaginary numbers it's when you're taking the square root of a negative number. Prior to talking about imaginary numbers, you weren't able to do that. We knew that the square root of 4 was 2, but you did not know what the square root of negative 4 was. Because when you think about it, what number squared gives you negative 4? Well, there is nothing, because only 2 squared gives you positive 4, and negative 2 squared gives you negative 4. So we're kind of out of luck. And so that's where this I comes in, and that's our imaginary number. The square root of negative 1 is I. And so by breaking this up into the square root of 4 times the square root of negative 1, now we end up with 2i. Square root of negative 25 is 5i, and just like the square root of 24 is 2 square roots of 6, because I'm taking the square root of 4 times the square root of 6, we end up with 2i square roots of 6. Now if square root of negative 1 equals I, then that means that I squared has to equal negative 1. Because remember that if we wanted to get rid of a square root, how I would do that is I'd square both sides. And so that gives me negative 1 equals I squared. So we're going to be using that once we work with our calculations. So complex numbers here are the imaginary numbers, and what it is it's taking a real number and an imaginary number and it's putting them together into the form of a plus bi. You have your real part, which is the a, and b is the imaginary. So if I have something like 5 plus 7i, the real part is 5, the imaginary part is 7. If I have 6 minus 3i, we've got the real part to be 6, the imaginary part to be negative 3. So what were we going to do with these? Well, first of all, we have to review our operations with them. The nice thing about working with complex numbers is it's just like treating it like a variable. When you are adding complex numbers together, we're going to add like terms. We're going to take 3, we're going to add it to 6. We're going to take 2i, we're going to add 5i to it. So 3 plus 6, that gives me 9. 2i plus 5i gives me 7i, and we're done. Adding them, you're adding like terms. When you're working with subtraction, we're going to take the real parts and subtract those. We're then going to take the imaginary parts and we're going to subtract those. 3 subtract 6, because we're subtracting here, is going to give me negative 3. 2i minus 5i gives me a negative 3i, and we're all done. When you are working with multiplication, we are going to use our FOIL method. So we're going to do first, outside, inside, last. And as I multiply, we're going to start out with 9 times 3, so that gives me 27. Outside, 9 times 5i, so that gives me 45i. Inside, 4i times 3 is 12i. And last, 4i times 5i gives me 20i squared. Now if I combine like terms, I get 27 plus 67i plus 20i squared. Now if we were just simplifying, working with variables, we'd leave it as that. The only thing is I squared equals negative 1. So if I take 20 times negative 1, I now have 27 plus 67i minus 20. And I can put 27 and negative 20 together to end up with 7 plus 67i. And there's my complex number. So I FOILed it out, combined like terms, and then I took that I squared and changed it out and put a negative 1 into the problem. Just to go through one more example here, I'm going to take negative 5 times 6, so that's negative 30. Negative 5 times a negative 5i is a positive 25i. 2i times 6 is going to give me a positive 12i. And 2i times a negative 5i is a negative 10i squared. So when I work out this, I've got negative 30 plus 37i minus 10i squared. Since I squared equals negative 1, I'm taking negative 10 times negative 1, which is actually going to be adding 10. So I have negative 30 plus 37i plus 10. Going to end up giving me here negative 20 plus 37i. So there's our adding and subtracting, and then we also had our multiplying. The last one that we have is working with the division. And when you are dividing, what you have to do here is you're talking about getting rid of the i's in the denominator. That's what we want to get rid of. And to do that, we have to use what's called the complex conjugate. The only way to get that I out of there is if you multiply this denominator here by the conjugate, which is going to be 3 plus 2i. And whatever we do to the bottom, we then have to do to the top as well. So the conjugate, if it's a plus bi, the conjugate is a minus bi. If it's a minus bi, it's a plus bi. So 3 minus 2i, the conjugate is 3 plus 2i. I'm just changing the one sign value. Because what happens is now I have to FOIL my numerator and denominator, and you'll see what happens in the denominator. 3 times 2 gives me 6. 2 times 2i is 4i. 4i times 3 is 12i. 4i times 2i is 8i squared. And then down below, I've got 3 times 3 is 9. 3 times 2i is 6i. Negative 2i times 3 is negative 6i. You see what's happening? And negative 2i times 2i is going to give me a negative 4i squared. Now you might be saying, well, wait, we still have some i's in our denominators. Not for long. So a numerator, if I change this out, this positive 8i squared is going to become negative 8. Put that with the 6. That gives me negative 2 plus 16i. And then down below, 6i minus 6i cancels out. And because that I squared equals negative 1, this minus 4i squared is going to be a positive 4. And now I have 9 plus 4 is 13. And there we are. So your denominator here, what's happening with the conjugates here is that middle term is canceling out, and your last term is becoming the opposite. And there we are. So why are we doing this whole thing with conjugates? Well, you're going to be coming up with possibly having to solve and get answers that are going to be complex solutions. So here I have an example of 3x squared plus x plus 2 equals 0. If I went through the quadratic formula and tried solving this, this is what I would end up with. Negative 1 plus or minus the square root of negative 23 over 6. Well, I cannot take the square root of negative 23, and so what it would be left with here is negative 1 plus or minus I square roots of 23 over 6. And there's my two answers. Well, with looking at this, if I were to start looking at what the graph is going to look like, and here it is, notice that the graph for this problem, if I'm looking for where are the x-intercepts, there are none. This graph here does not cross the x-axis, so we have no solutions. And that happens every once in a while. Sometimes with quadratics, you get two solutions. Sometimes you get one solution. Sometimes you get no solutions. You're going to get two solutions when that parabola is crossing your x-axis at 2 points. You're going to get one solution is if that vertex of your parabola is only on the x-axis. And you're going to get no solutions if your parabola is somewhere not crossing the x-axis at all. And though if you have zero solutions, that means you have two imaginary solutions. How do you know what solutions you have without even solving? Well, if you graph it out, that's your first instinct. Or you can look at the discriminant. The discriminant is the part that's underneath your square root of the quadratic formula. So the b squared minus 4ac, that's the discriminant. It tells you whether the solutions are real or imaginary, and it also tells you how many there are. If your discriminant is a positive number, meaning it's equal greater than 0, that means you have two real solutions. If that value is less than 0, being that it is negative, you're going to have two imaginary. If your discriminant equals 0, you're going to have one real solution. And how you're going to get one real solution and why not having two is, here's a quick example. If you end up working with your quadratic formula and you get 0, the square root of 0 is 0. And when I take 8 plus or minus 0 divided by 2, even though it's giving me two answers here, it's really not changing anything, and all I get is positive 4. So now that we're done here working with these quadratics, hopefully it's reviewed a couple things with the complex numbers. If you have any questions, make sure you write them down and let me know tomorrow.